like one of those apartment, it's like.
Welcome back, folks. Looks like we can get started. So we're just about done with the first week, just 15 more of them to go, and we'll be through all of it. But I wanted to mention before we get started today that if you really look closely at the Moodle website, there's weird things that happen, small changes here and there. The first one is we didn't finish section 7.1 on the date I indicated. We'll probably finish it today, very, very likely. So the due date has moved over by 1 day to Thursday, 1 week away from today. That's what will happen on all the assignments. It's always going to be a 1 week turnaround. That gives you the opportunity to ask questions, get support and tutoring services, those kinds of things, visit my office hours, implement your changes with Bryce off those office hours, and get enough time to do all that and send in your assignment. But the better way to think about this is it's good to just start working on these as soon as possible, because even if it's a different class, any kind of knowledge you put in your head, it has a shelf life. The moment you start working on this kind of stuff, mathematical skills, the better it actually really incorporates into your deeper long-term memory, the more familiar you become with it. But I realize everyone's schedule is pretty difficult. Some people might have to wait a few days before you have time to hit the homework, but just try to get into it as soon as you can. That way you can identify questions as they come up quite a bit as well and get help as needed, rather than starting late and then realizing you need some support with a short turnaround. But I should mention other things further about this. I don't actually have a late policy in this class. So something crazy happens in your life and you miss a due date, you can still get that assignment submitted for full credit. I do that to give a lot of flexibility because this is a really late night class. Most of us are pretty non-traditional students and that kind of stuff. But it also comes with this danger because you don't have the same exact pressure of getting zeros on everything that you might have not gotten in a time. So don't let that become a problem where you might get several assignments behind. This is a really hard class to get caught up in. The topics are pretty interesting. I was going to say gnarly or something along those lines, and they can be. So keep in mind, it's a pretty fast-paced 4 credit math class that sits right on top of Calculus 1. Sometimes this is one of those classes that takes the most amount of your time in a whole semester. But other times, if you notice, you're doing a little bit of reading before you come to class, hitting the homework assignments as soon as you can when the knowledge is fresh in your mind. You'll probably spend less time in this class because you don't have to go back and review as often. The knowledge is going to solidify a lot faster. So it's all about trying to get a good schedule going, a good routine and habit, and you'll do great in this class. Another weird thing that happens on the Moodle website is I never intended to finish section 7.2 on this week, but I posted it here because we'll probably open it up. But it's really going to be finalized on the very next week. And so that means I start moving things down. The files will land on the spot where the week where we're likely to actually finish them. And the due dates have to modify as well. So Thursday, January 30th, that doesn't look realistic. We'll probably be finishing that section when we come back after the holiday on Wednesday. So it looks like, well, it should have been the 29th. Well, actually, maybe that's a pretty good due date. We'll leave it the way it is. But any questions, folks, with those short announcements? Okay, our job today is just to jump right in and do a couple more integration problems. I don't have any applications in 7.1, 7.2, because really our major goal in chapter 7 is just pick up a few techniques. But I do have some interesting applications towards the end of this chapter. Chapter 8 is going to be all about applications, so we'll see a good amount in this course. But let's jump in. We're doing integration by parts, and this is a pretty interesting one. Usually when we use integration by parts, we're building out a table that goes like this. U equals dv equals, we pick for u something that's easy to differentiate, that becomes simplified once it's differentiated, something along those lines. And we might pick that. However, keep in mind this has its purpose. Any volunteers for what the mnemonic would say is the best choice for you? Absolutely. It turns out if you put natural log t here, far better way to go. If you put natural log t here, let me put it in pencil just to convey, this is temporary, it's going to be deleted. Natural log t here, you would come down and get your v, but that's integrating the equation above. And in the reading, the author does integrate this one. This is just integration by parts again. It's more complicated. It turns into x log x minus x, for example. That tells us probably not a good way to go. This looks like it's getting too complicated. But then, like we said again, the mnemonic is fantastic. It says, pick L logarithms. There's our logarithm, the natural log of t. Then for everything else, the everything else is t cubed plus 2t and the dt as well. That just goes over here in this expression for dv. So it is t cubed plus 2t dt. We need parentheses because dt in the land of differentials is considered an algebraic expression, which has to be allowed to distribute through to make this totally correct. So that's the start on this one. It's a pretty weird one because, again, the logarithmic portion of the integrand gave us a whole different approach here. But after that, it's pretty much just the process, following your nose, getting the rest of the results. Down the line, we convert u to du in the differential. Any volunteers for the derivative of natural log t? Good call, folks. That's a nice derivative, right? It just drops your variable t down to the denominator. Really short side comment. I do another derivative here pretty often. When a square root comes up, I often write 1 over 2 root x. This is just converting this to a power 1/2, dropping the power down. So here's your 1/2. New exponent is negative 1/2. Base goes into the denominator, and then you could give a root on it if you like. I feel like this one's kind of related to this in a certain sense. Natural log t on its derivative drops t down below. And the derivative of a square root happens so often that this is a pretty nice little shortcut to have ready to go as well. So if you see this used, don't hesitate to ask about it. I'll be happy to expand it out and show how we get there. But any questions, folks, with either one? Okay, well, the next thing we've got to do is come over here into this portion. Let me move this window a little bit better. There we go. So we need an antiderivative going from this equation down. It'll be v equals, and not so bad, we're just using the power rule here. So power goes up in the antiderivative. We counteract by putting a 1/4 on t power 4. So with differentiation, we eliminate the fourth. Same on this one. This will be just a t squared. Because we check this by differentiation, derivative of t squared gets us back to 2t. So with that table set up, we can write down, if it's helpful, the expression is going to be uv minus the integral of v du. So I think my u's are in blue and du, and green for v. This is the fun part of the problem. Once we have the analysis of what should be u, completion of these moving parts, you're just throwing it all together. So we now have, the answer is, for this uv part, we're just taking this part of the table, multiplying them diagonal. So we get, I'll put in the green part first, 1/4 t power 4 plus t squared times natural log t. Then after we're done with that part, this portion is asking us to integrate this right here. So we're just multiplying the last rows of the table, and that's pretty much the process. So integrate. For the v part, we're going to pull this in. 1/4 t power 4 plus t squared. And next for the du part. Oh, I do have a mistake here on the du part. There's one thing actually missing here. Good call, folks. It really should have a dt to be totally correct. In a real homework assignment or exam, I wouldn't take off a point over that, but I'd probably just write it in as a reminder. Not leaving it in can sometimes be okay, but it could cause real harm when we go to put together our integral if we have some problems with our variables. So let's go carefully. 1 over t isn't the whole thing for du. We also put in the dt to remind us what is the variable we're integrating, first of all. And I didn't format this too well, so let me see what I can do here. If this happens to you, you can always go and just break out a line like this. There we go. Now we've got a good 2-column system. From here on out, we just have to integrate this part, but that's a totally fine integral. We'll just simplify and then integrate term by term. So let's write out what we have so far. 4 t power 4 plus t squared times the natural logarithm of t minus the integral of, we're just dropping the power by 1 when we multiply by 1 over t. So it's a 4th t cubed plus t dt. So we've taken something that's really pretty complicated and we've eliminated it down to a calculus 1 integral right here, isolated to this part. Another thing that take away on this is you might have decided why not just break it up by going t cubed natural log t plus 2t natural log t dt. If you're thinking along these lines, you might have thought you could break this up now as t cubed natural log t dt plus the integral of 2t natural log t dt. It's sometimes a really good strategy, just break up your integrals in this way. But for us, it just means we'd have to do integration by parts twice. This is actually doubling the work. So sometimes you just want to leave things just the way they are. It's kind of strange. We figure out the best approach just by trying them out in the homework. We'll see where these kind of ideas come into play as we go to write these out. But let's erase this. This is just a comment to say, sometimes the natural thing you would want to do actually makes the work way harder. It's kind of weird in calculus. Well, the final result is going to be 4th t power 4 t squared natural log t. I'm just copying up to this point. Now we have a negative right here, which means we need to be careful. The antiderivative will have multiple terms, so we need a parenthesis here to allow that sign to distribute. Any volunteers for the next 2 antiderivatives? Absolutely. Thanks for those. Absolutely. So we've got our antiderivative. We added a constant c here. And now this is all up to you. Some people might distribute their negative sign through. That's totally fine. It's an equivalent algebraic form. Some people might distribute natural log through and the negative sign through. Yet another algebraic form that's equivalent. None of that would really combine or simplify in any kind of way. So the way you end your answer, it's all kind of up to you. The back of the book isn't the end all be all. If your answer is algebraically equivalent and simplified, it's just as good. Sometimes the answers in the back of a calculus book have lots of different ways they format them. And if you're just not sure if you need to go further, you can just send me a screenshot or a picture of your work, and I'll let you know if it's totally fine or, hey, you should distribute because something could combine, for example. But I would probably leave it personally right in this format. In fact, if you go to take a look at the homework sets, you can access them by clicking the 7.1 assignment. Click on the PDF right here. This is your actual homework set right here, just these problems that are listed out. The solutions I put down here, these are actually my solutions. This is where I would end my problems personally. Sometimes they match up with the back of the book because there's not a lot of variation in the answers. Other times, maybe for something like this one, there could be some different formats to the answer. And I just felt like there was no need to distribute cosine in. There wasn't any value into it for me. So I left my answer in that form. You yourselves are allowed to do that in your homework assignments. Just use good judgment on where you ended your problem on. If it doesn't seem like any value in distributing a sign in, then don't do it. There's no reason to do loads of algebraic steps when there's more calculus that we could be focusing on instead. So the thrust in the end of the day is about the calculus steps primarily for how these things are graded. I shouldn't scroll past this one just yet. Any last questions at all, folks, on this one before we move to the next? Yeah.
What did you do when you were all black for the first time? Where did the one half come?
Oh, let me see. Which part again?
When the integral part was like all the, when you changed it all the black.
Oh, down here.
Yeah.
So we had
On the right side part, the integral part, where did the one over t go?
oh, this part. Oh, sorry, I was having a hard time seeing that. So when this 1 over t distributed in, all it did was it knocked down that power right here. So algebraic, it kind of looks like this. A 4 t power 4, t squared, multiplied by 1 over t, turned into a 4th t power 4 times 1 over t plus t squared. And you can say times 1 over t or just divided by t, just however you'd like to format it. And then it reduced like this. A 4th, think of this as t times t times t times t. Divided by t just means t cubed is left over, plus t. So that was just distributing in. It effectively just knocked the powers down by 1 is what it did. Other questions about this problem so far? Okay, well, this is the main set of problems. One thing to note in the first part of our textbook is we're focusing a lot on the antiderivatives, so many of our integrals are just improper ones. But there will be definite integrals in the homework set, so we'll do a couple of them ourselves just to get a feel for how do you do integration by parts together with a definite integral. On one hand, it's just a matter of doing this. If this was from 0 to 1, get your whole answer, lob off the plus c, and just evaluate it from 0 to 1. So on one hand, you can just do your ordinary process, find the whole antiderivative and evaluate it. But that sometimes is kind of a weird approach, because when you do integration by parts, you're building your answer in stages. You can evaluate your answer in stages. That's often how our author does it. So let's do it here right now. So example 4 is evaluate this integral. It's going to be an integration by parts because of the product of the two functions, x times 5 power x. So let's go u equals like before, dv equals, and the last problem was tricky because there's a natural logarithm. That's almost always a good choice for u. But here it's an exponential function. Best choice here is just going to be x this time. So x gets thrown into this location. Then once you pick u, everything remaining, including the dx portion, goes over here towards dv. So 5 power x dx. And if you're like me, you might be kind of rusty on some of your derivatives. For example, we all know derivative of e to the x is just e to the x. But in a Calculus 1 class, you don't do these kinds of derivatives as often, it turns out. You differentiate 7 power of x. Anyone recall how this one should go? Absolutely. Sorry, what was the last part? Yeah, good call. Yeah, you could apply the chain rule on this one and end up in that answer. Absolutely. So yeah, that's the format for this thing. And so this is what it implies next. If you were to integrate 7 power of x dx, this is more relevant because that's what we're doing over here. You're just essentially doing this backwards. You would get 7 to the power of x. This time you're dividing by the natural log of 7 as opposed to multiplying, and then add a constant. Overall formula here is that the antiderivative of b power of x is itself divided by the natural log of b, add a constant. So that gets us through the worst part right here. We can now form the antiderivative of 5 power x. Any questions, folks, with the review stuff up here? Carter said, where did the 7 power of x come from? Oh, this was just kind of a related example before we went to our 5 power x example down here. So I just made this one up from scratch. So we're really mostly focusing on just this here. Oh, no worries at all. Thanks for mentioning that. That is kind of confusing. I probably should have just wrote down the formula first. And now that I'm thinking about it in hindsight, that would have been a little bit less confusing. Thanks for clarifying about that. Other questions so far? Okay, well, let's run through second row of the table. First column is always the easier one, ordinary differentiation. We'll go du equals derivative of x is 1, but it multiplies dx. Dx is just like an ordinary variable x itself. So 1 times dx is just dx. You could leave it like this if you prefer. Antiderivative here is following either this structure with a 7x example or this as the generic formula. We get v equals 5 power of x, divide by the natural log of 5. Now, let me actually format that slightly different. Because of calculus being sensitive to constants with the constant multiple rule, you know, it's sometimes a good idea to really pull that constant away so it's less of a distraction. Not always, but that can sometimes be a nice way to visualize the function. Then back over here, the answer is going to be uv, but it's a definite integral. What we can do if we prefer, this is an approach our author often takes, is evaluate uv from 0 to 2 the moment we find it. Then we go minus the integral of v du, but it's a definite integral, so this one is evaluated from 0 to 2 as well. So this is essentially the only new thing that happens in integration by parts if it is a definite integral. You just evaluate as you go. So let's drop in our values. We have a u here, v here, and du. So this now becomes x times, should have put that in front, but I'll get that in the next line. 1 over natural log 5 times 5 power of x. This is all evaluated from 0 to 2 minus integral from 0 to 2 of, grab v again for the second time, so this stuff, 1 over natural log 5 times 5 power of x. It says next times du, so we just put in a dx. But we knew it should have been a dx because x is here in the integrand, and we are expecting to integrate with respect to x. So we're running our way through it. We'll do the evaluation here, and one more antiderivative here. If you've done an antiderivative once, it's the same story the second time, except natural log 5 is going to be squared in the denominator on the next antiderivative. So let's write this out. Using the upper limit of integration, I'll plug in 2 for x's to get 1 over natural log 5 times 2 times 5 power 2. Do the same thing at the lower limit of integration, 0. If you're plugging in 0 for x, all of this just vanishes. So I'll just write minus 0 for short. Back over here, we're going to get minus 1 over natural log 5 to start. That came from the portion in green. When we do this antiderivative, we have times 1 over natural log 5 again. So let's just bump that power up to power 2. It'll be multiplied by 5 power of x, evaluated from 0 to 2. So all that's left to do is this portion, and we're on our way for the definite integral. Any questions at this stage? Okay, so one of the things that I sometimes do in this kind of formatting is when you go to do the upper limit of 2, lower limit of 0, you don't have to write this part twice. It sometimes saves you a lot of time in writing, makes your work a lot clearer, especially when there's multiple negative signs to consider, to put in an extra parenthesis like this. This parenthesis tells us we're going to put in 2 here minus a 0 here, and then just simplify this result, multiply by the expression in front. So this will turn into, let's see here, 25 by 2, so 50, divide by natural log 5, skip all the way to this part, minus 1 over natural log 5. We try again on that, natural log 5 squared. I'll put a bracket here to say, now we're doing the evaluation here. 5 power 2 minus 5 to the power of 0 And now we just need to simplify this portion. We're gonna get a result of 15 natural log 5 minus, I'm gonna take the part in the bracket, multiply it up into the numerator, so I'll just have a denominator natural log 5 squared. This is 25 minus 1 for a 24 up above. From here on out, it's up to you. I would totally just leave it in this format. I feel like finding the least common denominator, subtracting the results, doesn't really make this any more simplified. So this would be a natural stopping point. There is no plus c here. That's another thing to keep in mind. If it's a definite integral, the answer is just a number altogether. Kind of a strange looking number, but there it is. Well, we did it, folks. That's evaluating this kind of interesting definite integral. Big takeaway is you could have found the whole antiderivative and evaluated it, or evaluate as you go is what's normally done. But either way, it's going to give you the same answer in either case. Yeah, go ahead.
Walk through the steps of how you found the first derivative of 7 to the power of x.
Well, this one came from pretty much the formula. I'm noticing a line is going to be really helpful here for coming back to these notes. It pretty much came from this formula. Or wait, did you say the derivative or?
The first derivative of 7.
Oh, gotcha. That's a different formula altogether. It goes like this. D by dx, base b to power of x becomes the base b to power of x again, times the natural log of b. So by inputting 7 right here, here, and here, so that we are differentiating 7 power of x, we get 7 power of x, natural log 7. So it basically comes right from this formula. Other questions at the moment?
Looks like a log, the natural log of 5 to the natural log of 25 was equal, or
Looking down to say, which portion?
the natural log 5 squared.
This one, unfortunately, can't. This was a weird issue because if it was written like, say, this, natural log 5 squared, you absolutely can. In this land, we've got exponent laws for logarithms that go to natural log 5. But I'm glad you mentioned that because notice how sensitive this notation is. By putting an outer parenthesis here, what we're now saying is the result of natural log 5 squared, and this one cannot simplify, unfortunately. There's no logarithmic property for that one. Really kind of strange. Causes all sorts of issues for differentiation because natural log 5 power of x differentiates way differently than natural log 5 to the x power. They're totally different derivatives as well. Other questions so far? Okay, well, we've got exactly one more problem left to go on this set, so let's take a look at it. And I think I still need my reminder, we do not end at 8:07, so we still have about a good 30 minutes to go. I think this one is kind of a fun one in a certain sense. It's not an appropriate exam problem, but if something like this is asked in the homework, I probably really would give a hint when you go to pull up the PDF. So even if you have the most recent textbook, you might want to come and take a look at these PDFs because I sometimes do post hints on here, which is extra to what you'd see in the textbook. If I do that, I'll try to remember to actually also say it on the write-up, so it's not so easy to miss. So it says here, integrate that from 0 to 9, but start with a u substitution. Really kind of a bizarre problem. Let me just rewrite the problem here so we can work within our own notation. Cosine root x dx. It does not ask for integration by parts, so we're just going to follow our nose and do the u substitution. I'd say the best choice for you ought to be the square root of x. It's an inner function here. It's the only thing to really pick. But it's a mysterious problem because it doesn't really seem like this ought to even work. I would say the big purpose with this last example is just a reminder that u substitution is pretty exotic in a lot of situations. It's as complicated or more complicated than integration by parts, depending on the problem we're working on. So next step we have to take is compute, after we have this, the differential du Using the formula I mentioned before, if you differentiate the square root of x, you get 1 over 2 square root of x. Multiply that by dx and we're all set. And oops, sorry about that for the folks using the chat. Oh, the square of the natural log 5. Again, sorry for missing that question there, Carter. It came from this part right here. We already had natural log 5 once right here. So when we formed an antiderivative of natural log 5, another one of those popped out. So it came out to power 2 altogether. Does that make sense for where that part came from, Carter? Yep, you bet. Sorry for missing those chats as well. I'll get better at that as I go. If anyone in Zoom or in class as well, notice I missed one, don't hesitate to yell it out. I'll be sure to get right to that question. So down below, we have our differential. And notice this doesn't seem compatible whatsoever because there's no 1 over 2 root x anywhere here. But this is an ordinary algebraic equation. You can manipulate it, do substitutions on it, anything you want to it. So let's do that. Multiply by 2 root x to get 2 root x du equals dx. Now back over here, an interesting coincidence comes out. That root x is a u. So this turns into 2 u du is now equal to dx. Let's put all this together and just hope for the best on this thing. But maybe one additional idea, if you use this right here as your u substitution, there's a couple routes you can go. Oftentimes our author in our reading in Calculus 1 material and in the Calculus 2 material changes our limits of integration. So for folks who would like to do that process, let's show how it goes. It's not a requirement, but in a lot of situations, it does save some time. So we had originally limits of integration that x went from 9 to 0. So those came from the original integral. But we have a u substitution. These x's go inside u. So we're changing the variables as well. The limits of integration must change. So just visualize x goes inside here. It's now root of 9 for 3, our new upper limit of integration. This x value also goes inside here, giving us a root 0, coming out now as a 0. So these become our new limits of integration in the original integral. Does that make sense to folks? Did your prior instructor do that as well in this kind of coursework? Awesome. If you learn it in a different way, another approach is just to undo the substitution, use the original limits of integration. It's equally valid. You don't have to change your methods. I usually do it this way just because it makes the reading a little bit more compatible. Our author does the same kind of steps. So on the next step, let's put in all these interesting changes. First thing is new limits of integration are from 0 to 3. Now we have cosine. You can put in a little bit of extra space in front of the cosine. The root x, we're putting in a u. And last thing is this dx right here. We happen to have a formula for dx. It's this thing by the red dot, 2u du. I'll put the 2 here, forgot to give some extra space to put it, usually I drop it out here outside. Here's the u, and here's the du. I think arrows sometimes help convey that. So we've done all of our substitutions. Now we have this new integral. Let's reformat it. We're going from 0 to 3, and I forgot to do that again. Let me try one more time here. What I'm trying to do is just move this 2 out, so it's less of a distraction. We want to focus on the part of the integrand that matters the most, which is u cosine u du. So now if we can solve this antiderivative, we'll have the total answer for that definite integral. Any questions, folks, with the admittedly pretty bizarro u substitution method? Okay, The reason I bring this problem in is, again, a lot of times people are studying calculus 2 because it's going to be used in physics, engineering, chemistry, all sorts of different things. And when you go and look at U substitution in a physics textbook, when a derivation comes up, strange, crazy things like this does happen. Even in statistical textbooks, these kinds of things happen. So U substitution is a very flexible technique. It doesn't always get conveyed as well in calculus 1. But let's keep on going. We have now a new problem. This is integration by parts at this stage. So let's drop in a line to say, new set of work to tackle this integral. It's not a bad one, but it is a lot of extra work out of nowhere on this integral. So let's write out, well, we can't put u, can we? You could, but it would be an abuse of notation because u already emerged once. You might do something like this, u dot, or u hat to differentiate, or let's not say differentiate, that's a different word, to tell it apart from the other u. I think the better approach is just change to another variable. Let's go w and then dv. So this is w is playing the role of the u we've been using prior in integration by parts, only because we've used up u before. We can set w equal to the algebraic factor u. That'll make integration by parts work pretty well for us. That means everything else is just a cosine u. du. So we've got our table in line. Fast to fill out on this one, we'll have dw equals du. On this end, antiderivative of a cosine is just an ordinary sine. Derivative of the sine would come out as positive cosine, so we've got the right side in front. It's always a good check to make because when you're differentiating and forming antiderivatives, it's easy to get mixed up in your head where those negative signs are going. So just visualize taking the derivative. That's what we learned first and we're better at with the signs. Make sure everything works out and you'll be all set. So back to this problem. The formula integration by parts is going to be twice the result of uv evaluate from 0 to 3 minus the integral evaluate from 0 to 3 of v du. Oh, good call on that one. That was my mistake here. It's got to be a w. Thanks for spotting that. So w goes here and dw goes here as well. Good eye. Okay, so any other questions so far? Usually when one mistake appears, I'm suspicious there could be another one. Okay, let's get these values in. So I have a w going here, dw, v and v. This is the part of the problem where it starts to cool off quite a bit. We're just doing some ordinary evaluations. So first substitute. This is u times sine u for the wv part. Already kind of confusing because u does come in on this part. It got inherited from the cosine u portion over here. So u sine u is evaluated from 0 to 3. That's some weird values when we see the sine 3, but we're going for an exact result. You can just leave your answer sine 3. Then go minus, integrate from 0 to 3, sine u du, but just by following the color coding, dropping in those results. Now, last steps, one more integration, one evaluation. We've got twice the result of plugging in 3, it's 3 sine 3 minus, now plug in 0 here. Really, we don't have to say much. Sine of 0 is 0, but it's also being multiplied by 0. I'll just write minus 0 as a reminder. Yes, we didn't forget that part. Over here, we have a negative sign. We want the antiderivative of sine. Looks like the antiderivative should just be plus cosine. That's tricky because if you're just looking at this part of the problem, that looks totally wrong, right? Antiderivative of sine is negative cosine. But there was already an extra negative sign right in front, so we really do have the right value. Differentiate cosine, and you get, here's the negative times sign we're expecting. Then this evaluates
Professor,
for, yeah, go ahead.
does the square root of x ever come back into play? Because wasn't u originally the square root of x? So would we have to substitute 3 into the square root of x before we put it into sign?
Not quite, because we also change the limits of integration as well. If we change the limits of integration from the original 0 to 9 back down to a 0 to 3, we keep
Oh,
the
we don't
same
change it back then.
Exactly, yeah. But if this was a 0 to 9,
Okay.
we would have had to undo it in that case. Absolutely. So
Okay,
0 to
great.
3,
Thank you.
yep, absolutely. Oh, and sorry, it looks like I missed a chat as well. So you just separated the 2 du so the 2 could be moved out. Yeah, absolutely. I wanted the 2 to come out in front of the integral right here. So I put in this 2 du, dropping the 2 to this location. Other questions at the moment? Okay, thanks for the questions so far. And yeah, that is also really pretty weird with this kind of method. If we ever change the limits of integration, we just stick with a new variable. Maybe another way to think about this, I think that helps is when we say 0 to 3 here, but we also said u goes from 0 to 3, that's also a reminder we're sticking with the original variable u in our evaluations because we expressed that's the right value to plug into u to move forward. Now we're just about through this. Let's rewrite. Our answer is now 2 times 3 sine 3, new evaluation and another weird value, plus cosine 3 minus cosine 0. One thing I want to mention here on the notes for the course is we should evaluate all of our trig functions that are easily evaluated to exact values. So we must evaluate cosine 0 equals 1. However, for sine 3, we would evaluate it if it was sine pi, or maybe sine 5 pi over 6, 7 pi over 6, something like that. There's no great exact value for this one to write down, so we just leave this in its exact form. Leave in exact form. So really the only last thing we've got to do on this thing is just write out only the 2 distributed on the outside, 3 sine 3 plus cosine of 3 minus 1. If we want to give people the most accurate possible expression for integrate from 0 to 9 of cosine root x, it is that stuff down below here. Sorry for the random scrolling on that. No harm if you want to also approximate it. Sometimes it's not a bad idea because it can give you an intuition. Is this answer even in the right ballpark? Are we expecting this? So let's approximate it just because sometimes that's not a bad idea. Pick out your favorite calculator. If you do have your calculator with you today, make sure it's in radian mode to match up the answers. Essentially anything in calculus, if you're dealing with a trig function, the assumption is automatically that's radians unless you put a degree unit on it. So it's twice 3 sine 3 plus cosine 3 minus 1. I'm not super familiar with Desmos, so what I would do to make sure I'm in the right mode is just go cosine 0, which should evaluate to 1. That gives me confidence, yes, we're in the right mode. If you ever needed a change in Desmos, I think it's something over here, potentially. Yeah, radians to degrees, massive change on your answer. So you should be getting a negative answer. Let's put in negative 3.133. I want to use this pen just to convey this is an optional step. Then imagine you're doing this as a homework problem. Part of the reason why you might want to approximate is just to see if your answer is even reasonable. So let's plot our problem. It was cosine root u from 0 to 9. So f of x is cosine, I said that weird, it's cosine square root of x. There's cosine square root of x. This is not quite the right domain, so let's also put here another expression. 0 less or equal to x, less or equals to 9. And this is what we're integrating. The fact that we got a negative answer now makes sense. Integration takes the signed area positive here, adds to it the signed area negative here, of which there is quite a bit more. And so we should get overall net area negative in this problem. So we did it, folks. That looks like a very accurate answer. And this is a pretty nasty technique having to do multiple methods at once. But this does happen sometimes in a calculus class in Calculus 2. So that was another part of this problem right here. I don't have anything as long as this on the real homework assignment. But again, it's just another way, this problem, to take a look at U substitution. I think we're done with this section, folks. We did it. We did section 7.1 in about 2.5 days. That's because we're just getting started, doing a little bit of review at the same time. Any questions whatsoever before we go off to the next section? Okay, let me save this up. If I ever forget to save and you notice solutions are missing, when I go to upload them back to the Moodle website, let me know right away. I'll make sure to get those solutions in. Sometimes just weird things happens on my thumb drive. I guess files get corrupted, stuff like that. And you know, when we change a section, it's like a small breather. That's not a bad thing sometimes. So all the files you see here are always duplicated exactly in my thumb drive. And here's our next section. Trigonometric integrals is now a great opportunity to review a couple things, derivatives of trigonometric functions, because we're more interested now in their antiderivatives. For this table here, one way you can kind of think about that helps out is there's a definite order in which these negative signs are propagated. When you differentiate a cofunction, you're always going to expect a negative sign. And if it's not a cofunction you're differentiating, you're expecting a positive sign on these kinds of things. So that's kind of a nice, helpful pattern. Doesn't quite convey as well when we come down here. And by the way, these are some pretty crazy integrals that we're taking a look at. It says antiderivatives of trigonometric integrals. C is an arbitrary constant. We know the antiderivative of sine is negative cosine. Calculus 1 may or may not have done this problem, but this one is a U substitution. You have sine divided by cosine. You let U be cosine, and you get this right here as a result. But what about these ones? To me, these are pretty weird, bizarre antiderivatives. Trying to derive one of these is not completely the funnest thing in the world, but it could be something that's worth giving a try. So we'll try that out next. Let's try to get the antiderivative of secant x, and then the result for cosecant x would be highly similar. Any questions before we get started on this one? Okay, so antiderivatives of secant x. There's more than one way to try out this process. And if it was me trying to discover this for the very first time, it feels like it would take 100 years to come up with this trick. But someone eventually tried it and it got them the answer. Let me see if I recall how it goes. Take your ordinary integrand, secant x, and you want to multiply it by the number 1, written in this excessively complicated way. It's going to be secant x plus tangent x divided by secant x plus tangent x. So I'm not changing anything here. This is just multiplying by 1 once it reduces. So next thing we can now do is I'm going to distribute this secant into the numerator. So we now have antiderivative of secant squared x plus secant x. Let me try to fix my penmanship on that. times tangent x. And by the way, with trigonometric functions, I usually do the normal thing and not put parentheses in the function notation. Unless I'm jamming a lot of stuff together, I like to put a parentheses there to say where the input of secant ends and a new function begins. But it is an optional way to format your answer. Then down below, secant x plus tangent x dx. So our goal is again to derive this antiderivative. These two are just ordinary u substitutions. These come from your differentiation table above. If you can solve this one, same trick works for this one. So let's restrict our attention to that monstrosity of a mess. Turns out the way to get through this is just a u substitution. To pick a u substitution when you have a fraction, you always want to get the denominator, because there's no value in grabbing the numerator, differentiate it, when you want to take out stuff that is somewhere else. So if you let u be your denominator, secant x plus tangent x, we'll form the differential of this whole thing, and we hope it becomes this stuff upon doing that. So let's give it a try. Du. First, it's the derivative of secant x. That's a pretty bizarre derivative. It becomes itself times tangent. So secant x, tangent x, plus derivative of a tangent is a secant squared of x. Then close the parenthesis and throw in your dx. Now taking a look at this, we do have secant x tangent x, and we do have secant squared. So miraculously, somehow, some way, this bizarre approach really works. We've created a situation where u substitution can be maneuvered. And by the way, section 7.2 is almost exclusively u substitution. I think I put integration by parts just in a couple places, just so that we can practice that a little bit more and not forget about it. But this is primarily what we're doing in this entire section, just a bunch of u substitutions. Here's how it's going to go. Everything here in that denominator, that's just u. The numerator is completely wiped out. Everything highlighted in green now becomes du. Let me just fix that, number one. Certainly, that's a nice antiderivative. It's going to be the natural logarithm of the absolute value of u plus a constant. This is the most bizarre antiderivative because this is the one that doesn't even follow the power rule whatsoever. So this is the only time u to a power becomes a logarithm. Next, we just throw in what u was. So we get natural log, absolute value, secant x, plus tangent x, plus a constant. Then at that stage, we've got it, folks. Let's see if we really have it. Secant x plus tangent x and a constant. So that's how this antiderivative is formed. Not the only way to do it, but I think it's the fastest way. It just looks really bizarre and ugly when you get started on it. So any questions at all, folks, on running through this one? Absolutely, yeah. For doing cosecant here, I'd be multiplying by cosecant x plus cotangent x, above and below. I might have to change the sign to negative. I would have to double check that as I gave it a try. So I might have to do a couple tries on that one, but very similar in spirit by using that main approach. Other questions so far? Okay, so now that we have that result, main idea was just to give some sense to some of these formulas because they really look awful the first time you see them. If you can derive one of them, at least it feels like you press the I believe button. The formulas make more sense. They become easier to use if they don't look strange. So that's the purpose of using this. For some of these things, like if we were doing an exam, I would probably print some of these results on a formula sheet. Let me highlight it this way. I think on a formula sheet for exam 1, I would include these results, but these are considered carryover for calculus 1 that we should be ready to go with at a moment's time. Same for the table above. We should always be ready to calculate those derivatives. So these wouldn't be included in the actual table or formula sheet at the end of exam 1. Well, we got through the main thing. We have just a little bit of time, about 13 minutes. Let's see if we can take on maybe one problem and call it a night. I don't want to try to break a problem in half. That one looks like it could take more time than I have today so far. So we'll do this one, go on a big long holiday, and come back on Wednesday's class. First thing I want to mention is I typed this out verbatim from the author's textbook. And sometimes people do like having a good strategy to use. But the bigger takeaway here is these trigonometric identities, we do have some options to use them here and there throughout this section. And even more identities you should be ready to go with are these ones right here. You know, it might not be a bad idea, in fact, to, as you do set this current section we're in, just to have this ready to go. It doesn't have to be this sheet. You can just Google trigonometric identities and you'll get pages of great tables. So pick your favorite one. But we'll be using this enough. It's just good to have at the ready. In particular, you'd be surprised how many times in Calculus 2, the first 3 come up. It's quite a lot, actually. So I'll put this here just in case we need it. There we go. And now my next thing to mention here is, in practice, a lot of people don't even try to memorize this. You might use it in your homework, but when it comes to an exam setting, I feel like this isn't terribly helpful. What you really want to do in a problem like this one is just do an ordinary U substitution and try something that makes the most sense in the problem. So let's show how this goes once. But when we go to do the other ones further down, it's really just ordinary U substitution. We'll show how to do it in a more natural way where you're not looking at a large 3-part strategy guide on getting through it. When it's really just amounts to either pick cosine or sine squared. And the more we do this, the better we are able to at making an informed choice. But let's take a look at what this is all about. On the next thing to focus on, it says, if the power of cosine is odd, I guess the whole thing is highlightable there. We're going to save one cosine factor, use this trigonometric identity, and use that substitution. So this is basically the whole strategy. Power here is odd on cosine, so the best substitution to use is sine. So to me, that's the big punchline. There's also a potential identity that we might need to use. Same idea over here. If power of sine is odd, then go to the opposite factor, cosine, and make that your u. Let's give this a try with the one that was picked out for us by this strategy here. If u is sine x, then du is going to be cosine x dx. Notice it looks like we're pretty much in business then. We don't even need to make use of this identity, but in a lot of problems, we will have the option to do so. Very next example looks like. So that's the u substitution that works for us. But you know, it's equally important to know when a u substitution doesn't work. Let's put that down here as well. If you did try the opposite thing, say u equals sine x, or excuse me, that's not the opposite thing at all. Let me try one more time. If we tried u as cosine x, then we would take du equals negative sine x dx, which means you lose one factor of sine right here on the approach to the far right. It leaves one factor of sine alone, and we have nothing we can do with that. So that's the whole problem with this approach. One sine factor is left over, and there's no way to remedy that. So this doesn't work, but this one will, because if u is sine squared, is sine x, we have u squared here, and this whole part right here is now du. So this approach does in fact work. So here's sine squared x being substituted out, and cosine x dx being substituted out by du. Now, again, this is a portion where it's pick your own adventure, where you can change your limits of integration or leave them exactly the same, for which you have to undo your substitution. let's leave it up to the class. How should we do it this time? Change limits, undo the substitution. Any volunteer for a direction? Let's change them. Good call. It's the more standard approach. It makes the book more readable if we get into that kind of habit. And to be totally honest, when the problems get really long, 7.3, and there's 2, 3 substitutions going on, you don't want to undo every single substitution. That's actually a lot of work. It's sometimes just more efficient to change as you go. So here's how we do it. The variable is x, and there's 2 quantities. Try to keep these in the same order because we don't want to accidentally flip which limit of integration goes where. So try to keep pi over 3 on top, 0 below. We're feeding these quantities up into the sine function here. So first it's going to be sine pi over 3. Let me write this out this way. Sine pi over 3, which evaluates to square root 3, divided by 2. Next one is going to be sine at 0. Sine at 0 itself evaluates to 0. So those are our new limits of integration. And I wanted to put one more additional thing here. I forgot. It's not a bad idea to describe this as u equals, to remind yourself this is the new limits of integration for the variable u now. So this is now equal to 0 root 3 over 2. The sine squared we were looking at becomes u squared. So that's kind of a nice thing to have in the integrand. And the cosine x dx highlighted in green is just a du. So we've transferred something that's a pretty difficult integral to look at. This one could have been done in Calculus 1, but I think they often leave this for Calculus 2 for us to work on. So we took something that's complicated and we reduced it down to a Calculus 1 type integral. That's basically our strategy in chapter 7 for almost every section. Reduce it down to something like that, where it's now attackable. Antiderivative here is a third u cubed. I'm associating the u cubed part because you really only need to write a third once in your evaluations, which go from 0 root 3 over 2. So we're going to get a third. First, we're cubing root 3 over 2. That looks pretty ugly if you wrote that down just like this. But, you know, I wouldn't be too opposed if you did leave your answer in that format. It simplifies a lot, but I'm not as worried about the arithmetic simplifications as I am in seeing the process of getting the antiderivative and evaluating it. So this one would be okay to leave in that format. Then minus 0. And you could leave your answer just like this. But exponent laws never go away. So let's simplify this just because we can. You do have options here, so let's go and take the option of doing just a little bit more. Cube square root of 3 halves to power 3. This is how I would probably evaluate it. I would take the cube root of 3, transfer this into exponential notation, and keep on saying that wrong. That's the square root of 3, not the cube root. I think the 3 is throwing me off there. The square root of 3 becomes 3 to power 1/2. Raised to power 3, there's too many 3's here, then 2 to the power 3. So that means this is turning into 3 to the power 3/2 divided by 8. And you know, even this simplifies if you wanted to. But let's write our total answer as a third, 3 to the power 3/2, 8, which means we get altogether 3 power 3/2 over 24. So much more you could do to that number. You could reduce 3 to the power 3/2. You could combine the base 3 here with the base 3 up here. There's like as many different ways to format this answer as there's people in class today. But as long as you've got the right exact value, I'm not too worried about equivalent arithmetic forms or algebraic forms. Any last questions at all, folks, on running through this? Okay, we started off with a definite integral right out of the gate, but on a lot of them, we're going to see down below, they're going to be primarily indefinite integrals. We'll return to more of these kinds of problems when we come back on Wednesday's class. But have a great weekend, folks, a great holiday, If you do have any questions over the longer weekend and holiday, don't hesitate to email. I don't check my email all throughout the day, but I always check it every morning as pretty much a ritual, so I'll always get back to you. Take care, I'll see y'all next week.
Have a good day.
Thanks, you too.
Yeah.
Sure. Yeah.
So I'm on this first one, and in the answer key, it's 1/4 X sign 4X and then 1/16.
Oh, I see, yeah.
Where I'm missing, because I know you're multiplying another 1/4, but I'm just, where am I missing the 1/4?
Gotcha. So you got the right value here. That's
Right.
awesome. So we can go X to this. It should have been X times the 1/4 sine X. So you have an extra 1/4 right there.
You're right.
And then this 1/4, when you come back to, let's see here, that location it goes in,
Okay.
and that'll get you
Like,
your
what am I
16 back.
doing wrong? Thank you.
That happens to me all the time. I forget to copy little things down. Yeah, I'll do that like a million times in class, so no worries. Yeah, cotangent squared is a fun one. I think you would want an identity on that.
That one was on the homework, I was just.
You'd want to go like this. This is kind of a nasty one in a certain sense because cotangent squared x, we need an identity that goes cotangent squared x plus 1 is cosecant squared x. So now we can rearrange and say, I forgot my dx there, that this is cotangent squared x is now equal to cosecant squared, exactly, -1. And we have an antiderivative ready to go for the cosecant squared,
Yeah,
but not for cotangent squared.
yeah, no, I just didn't know how to do it. I looked up
Gotcha.
like a way to do it, but they went the really long way around where they split up the cotangent to cotangent
Oh,
and
weird.
cotangent
That is
And
pretty
then-
bizarre, actually.
and then derived it that way.
Mhm.
I also have another question, because
Yeah.
on the homeworks, you start integrating tangents and secants.
Mhm.
One of them, it was like secant, it was a odd secant power.
Like secant power 3?
Yeah, and then it was like tangent, or the secant to the 6th, sorry.
Oh, secant 6.
Yeah,
And what else was there?
and then it was like a tangent, either the two problems were tangent to the cube and tangent to the 4th.
Gotcha.
But I was just wondering, like, couldn't you use the same techniques? Because this secant squared, you could separate it and make it into what was it, 1 plus tangent squared,
Yeah, absolutely.
and just do it that way, but when I tried doing it, it didn't work out, so like.
So let's put one in and just see what we can do with this. I put in a cube for tangent. So if it's a cube there, let's see. One thing that you could try with this is oftentimes, if you're not sure what the good u substitution should be, try out the one with the highest power.
Okay.
Because if that works, that's going to be the easiest approach anyways. So let's let u be secant x. du is going to be equal to secant x. That means we're actually pretty good because we have to give away one factor of tangent here. This is turning into secant power 6x.
Tangent squared.
Yeah. Oh, and I should drop that down to a 5 because I need to give one factor away there too.
And then you could rewrite.
The-
And wouldn't this be u though? U to the 5th.
Yeah, this is now going to turn into u fifth, either now or later.
And then you could rewrite the tangent squared as 1 plus secant squared, right? And
Exactly.
get u's there, and
Yep.
then just distribute the secant squared and just make them all into u's.
Yeah, that's pretty much how this one's going to just fall over and get
Really?
integrated.
Yeah, no, the problem I did, it was like super interesting. It was.
Yeah. There's some in the homework where depending on what your u is, it can either be a tangent or a secant.
Mhm.
And now you have two algebraically equivalent answers.
Yeah, because here I changed the secants into
Mhm.
the 1 plus tangents, and I left the secant squared because I knew when I used U as tangent, I
Mhm.
would get a secant squared here. And then I get that,
Yeah, that looks like the right answer.
but then here, I tried to do the same thing,
Mhm.
and couldn't you do the same thing here?
Yeah, that's the one we're doing right over here.
Yeah,
So same kind of approach, break up your tangent squared as an expression of secant.
mhm,
That'd be secant squared minus one.
mhm. Okay, thank
Yeah,
you.
that should work out just fine for that one.
Yeah, no, this took me like, there are so many where I was just happy to remember the trig identities.
Yeah, trigonometry is one of those things where you finish it, it's so many formulas, so it leaves your head fast, but it just keeps on coming back. Calculus 3 is
Yeah.
tons of it as
I'm
well.
already trying to memorize the identities, like the double angle identity.
Oh, yeah,
It's two sine, cosine, at least for sine 2x, it would be two sine times cosine.
yeah,
And then for cosine, it's sine squared minus cosine squared or something.
it'd be the other way around.
It'd be cosine squared minus sine squared.
Yeah, but then there's like 3 other versions of that, so you can write down your double angle for cosine a lot of ways.
Also, how does the half angle one work? Cause you could rewrite, you could say sine squared is equal to 1 minus cosine over 2.
So for half angles, well, this is not quite a half angle idea, this is a reduction formula.
Well, that'd be
Um,
the half angle, wouldn't it?
Which
Oh,
one?
no, I know, yeah, you're right, it wouldn't.
Let's see here, I definitely got some identities here. Let's take a look. Reciprocal quotient, these are always kind of nice. And here they are. Here's the half angle identities from the last book I did trigonometry with. It's in deriving these things, I believe what you do is you use one of these forms. You solve by isolating, say, your sine squared, taking the square root, and you do a transformation on the variable. This becomes theta to 2 theta. Notice that essentially what's happening is here to here it's doubled,
Mhm.
here to here it's doubled. So that's just a change of variables, actually.
Oh, so that's where they get the sine squared is equal. Okay.
Yeah, and that's why there's a plus and minus, because they took the root of sine squared.
No, that was throwing me off. Like, cause I used that in I knew that it worked, but I didn't know why it worked. And I was just curious about.
Gotcha.
Yeah.
Pretty much all of these identities come right from here, sum and difference identities.
Yeah.
And everything just gets derived out of that. It's weird.
Yeah, no, thank you.
Yep, absolutely.
Very much. I'm sorry that I was that question.
Oh, no worries. It's good to be curious, right?
Yeah.
If you're not curious about the content, it's hard to remember the stuff because then your brain's not excited about it.
Well, I had Randy last year for top one,
Awesome. He's a great guy.
and he would always go over how it came about, whatever we were using,
Mhm.
why it works. I did actually enjoy it. I
Yeah,
know it was a lot of boring technical, like.
it
higher
really
level
is.
math, But it worked.
If you could give your brain like a path of why this is true, it's like your mind likes a good story. You internalize that and then you're really memorizing those results very well at that point.
All right, thank you.
Yep. Have a great weekend.